This lesson is about the central limit theorem for means. First, consider the following example. ACT is a college entrance test given nationwide. It turns out that ACT scores are normally distributed. The average score is 21, and the standard deviation of scores is 5. So if we were to look at ACT scores, it's certainly possible that an individual could score average, slightly below average, slightly above average, or even far below or far above average. These are all in the realm of possibilities. And if we were to continue to look at individual ACT scores, eventually we might get a distribution that looks something like this. As you can see, this distribution is normally distributed, as shown by the bell curve here. Notice that each of these dots represents an individual score. What if we were to do something different? Rather than look at individual scores, what if we were to look at sample averages of 15 random scores? Here's what I mean. Here's 15 random ACT scores. I computed their average, and I got 20.4. I could place that sample average here on my distribution graph. But would it be possible to take 15 different randomly selected scores and get a sample average that was different the second time than the first? Well, of course it's possible, and likely in fact, because samples tend to vary. Here's another 15 randomly selected ACT scores. This time the average was a different number again. Now if I were to continue to pick 15 random ACT scores, compute their average, and each time I computed it, plotted on my distribution graph, eventually I might get something that looks like this. We call this a sampling distribution, and notice that each of these green dots represents a sample average of 15 individuals, not a single individual. So now, what does the central limit theorem for means tell us? Well, the central limit theorem is really three statements. Statement 1, if my population is normally distributed, then my sampling distribution will also be normally distributed. Statement 2, the average of my population and the average of my sampling distribution are going to be the same number. Now this bottom average is really an average of averages and has this lengthy name, so we tend to call it mu x bar, reminding us that it is the average of sample averages. Statement 3. Whatever our population standard deviation is, will be shrunk down when we compute the standard deviation of the sampling distribution. The standard deviation also has a lengthy name, so we tend to just call it sigma x bar, symbols which remind us that it's the standard deviation of the sample averages. So if this figure gets shrunk down from the original standard deviation, how much does it get shrunk down by? Well, it turns out it gets reduced by a factor of, in this case, radical 15, because 15 was my sample size. So, let's generalize. In general, if I have a population that's normally distributed, the central limit theorem states that my sampling distribution will also be normally distributed. The central limit theorem states that the averages will be the same, and that the standard deviation will be shrunk down by a factor of the square root of my sample size. What if my population distribution is not normally distributed? Does the central limit theorem tell us anything about the sampling distribution? Well, it turns out it does, provided that the sample size is greater than or equal to 30. And if it is, the central limit theorem makes the same three predictions. 1, my sampling distribution will be normally distributed. 2, the averages will be the same. And 3, compared to the population distribution, the sampling distribution's standard deviation will be shrunk down by a factor of the square root of the sample size. And that completes the lesson.